We're really excited to have Claude coming to speak to us today. So Claude Formanek is a PhD student at the University of Cape Town, specializing in offline MARL. He's also a research engineer at InstaDeep, focusing on RL for industrial optimization. Claude's going to speak to us about improving the quality and the rigor of offline MARL. So if you went through Claude's paper, you'll see that there's some surprising inconsistencies with certain state-of-the-art offline methods, and that simple, good baselines can actually get you quite far. So he argues for improving the quality and the rigor of offline MARL. He also speaks about datasets and some challenges with inconsistencies in datasets, and proposes a standard repository to help with this issue. So I'm going to hand over to Claude. Thanks so much for joining us.
Cool. Thanks so much, Khalid. Yeah, thank you very much that I was invited, and I'm very happy to speak and share the work me and the team have been working on for quite a while now. So yeah, this is basically work which started in 2022 as I embarked on a PhD at the University of Cape Town. And along the way, I've had some amazing collaborators like Louise and Callum, my supervisors, Professor Jonathan Sharp from the University of Cape Town, and my supervisor from InstaDeep, Dr. Anu Pretorius. And Callum was at this very lab, so hopefully he's maybe around. So yeah, this is going to be a sort of long and winding tale of how we've worked towards standardizing data sets and baselines in the field of offline MARL. So just a quick primer first on what is offline MARL. So this is a diagram which should feel a little bit familiar to anyone who's worked in multi-agent RL or RL in general, with a few details that are important. So in purple on the left is kind of the environment we're interested in, multiple agents or policies, pi, interacting with that environment. We subscript beta to indicate that these are the behavior policies that we're interacting with the environment and we were recording. And so that could be humans interacting with an environment and you record that, or indeed like previous reinforcement learning agents interacting with the environment. And then all those transitions are stored in a big offline data set. And then after that is all done, you then begin training a new set of offline, this is a new set of policies pi for each of the agents on that data set alone. Now the bottom feedback loop, which, you know, in your typical on policy or off policy RL loop, you would then periodically send your agents back into the world to collect more data and add it to your replay buffer. But in the offline setting, we're assuming that this static data set of experience, you know, we had beforehand, and you can't add to it during training. You just have to train on the fixed data set. And then all the way at the end of training, you deploy your policies into the world, and you hope that they learn something reasonable. Yeah, so that's offline MARL. It's the sort of intersection of the established multi-agent RL field, and then from the single agent literature, the offline RL field, which, yeah, when we set out sort of in 2022, there was very little work at this intersection, but more on that just now. So how do you do offline MARL? Well, I wanted to give like the most naive or simple algorithmic idea you would think of if you just started, namely to take a single agent offline RL algorithm like conservative Q-learning, and then just independently do that for each of your agents in your MARL system. So let's just call that independent conservative Q-learning. And conservative Q-learning is a very intuitive idea to understand for anyone who's not used to offline RL. Basically, in offline RL, the main problem is that RL agents will typically overestimate the value of actions they haven't seen in the data set before. And this has to do with, you know, in your Bellman update, that max operator, it favors high values. And so if your neural network happens to assign a very high value to a action it hasn't seen before yet, that'll never get corrected in offline RL, because you'll never collect samples, more samples. Like in the online case, you would typically go try that action out now because you've assigned a high value to it. But in the offline case, you don't get to go test out your hypotheses. And therefore, that erroneous high value is then propagated through your Bellman update to all your other state action pairs, and eventually everything just falls down. So your agent will tend to then choose those actions explicitly rather than avoid them, because there may be a good reason that those examples aren't in the data set. Like there are probably few examples of humans veering into the oncoming lane of traffic, and that's for good reason. But you may find a naive offline RL agent would do exactly that. So conservative Q-learning tries to mitigate this by putting a regularizer into your loss that says push down the Q values for actions I haven't seen yet. And in code, it's very easy to do this for discrete actions, at least. In the continuous action space, it's like slightly more complex, but also not hard. You add in this term, the CQL loss term, where you do log sum exp over all the action dimensions. So if you have 10 actions per agent, log sum exp over that dimension. And that has the effect of any Q value that's really high will be penalized the most. Okay, but now because the Q value for the action that was in the data set is also in that term, you need to add this minus replay action Q values to just say like you are allowed to push Q values up for actions that are in the data set. And then these things together, you just add to your normal TD error loss, the standard DQN loss you were doing with a like weighting term. Sometimes people like automatically tune that weight, but if you do that, then you learn a conservative Q function. Sorry, I just want to open a window. Yeah, okay, so we independently do that for all our agents, and then you have an offline MARL, like your simple offline MARL algorithm. In continuous action spaces, probably the most simple algorithm to understand is an independent version of TD3 plus BC. So there was a paper called A Minimalist Approach to Offline RL, and they just proposed this algorithm TD3 plus BC. So you should be familiar with TD3 from RL. Plus BC means you just concatenate this term to your loss that says try to behavior clone like what you see in the data set as well. So the last two lines is literally all you have to add to your TD3 algorithm, and then boom, you have TD3 plus BC. So you can just do independent TD3 plus BCs, and then you have a naive offline MARL algorithm for continuous action spaces. So yeah, the field of offline MARL circa January 2022 when we started literally had, like in deep offline MARL, 3 papers. That was them. So these papers basically only used a couple MMUJOKU environments for their continuous action space experiments, a couple SMAC environments, and then like one of them used some MPE environments. But then there were big sort of problems here. Like you tried to get the code, it was like in the case of the first one, not available, and the data set wasn't available. For the MAICQ paper, they did provide the code, but the data sets, like quite soon after they shared a link, stopped working. And then the OMAR algorithm, they did share the code for the like continuous version for MMUJOKU and the data set, but not for the SMAC, like discrete one. So on top of that, like each of them made their own data sets, so there was no sort of like standard axis along which to compare them. So what we began with was to try and standardize across these few papers by introducing some really high quality data sets, first on SMAC and MMUJOKU because they were widely used, but then like wanted to push further to these other environments. So we included Flatland, the sort of train environment, and then 3 environments from Petting Zoo. and we generated different data sets on different scenarios and stuff. And we released the utilities to like make your own data sets. And then we did a whole bunch of benchmarking on those data sets. So we, in the case of MARL and MAICQ, because we had access to at least some of their code, we, like, as faithfully as possible, reproduced their implementation and got it to run, and then reported those results. And then, yeah, so the MAICQ algorithm did really good. I mean, okay, these plots are, they're too small to look at carefully, but take my word for it. And then the MARL algorithm, like, did not so good. And then we implemented our baselines, namely the ones I explained to you in the beginning, sort of like our naive baselines. And they were both like pretty competitive. And that culminated in this paper that we then submitted to ARMAS, and it got accepted as an extended abstract, which was really cool. And at the time, I got to spend some time with people from this lab because it was in London, and they were kind enough to sort of bring me into the fold. So that was great. Then what we did from there was try to expand it. We added in like a whole host of additional data sets, added in SMAC v2, the CityLearn environment. We then expanded the amount of benchmarking we did. But unfortunately, that got rejected when we submitted it to the NeurIPS datasets and benchmark track. And why did it get rejected? Ultimately, it came down to this one column in the appendix of our paper, in which the MARL algorithm, the one from the literature that we try to re-implement, did like bad. And the reviewer was insistent that it ought to beat the like TD3 plus CQL one, despite MARL, like in the original paper, only being tested on like 2 half cheetah in any case, and like their own data set, not our data set. And like there were just so many sources of why, this is totally could have been valid, but the reviewer didn't want to budge. Tried to request us to like remove the column, and we declined, and then ultimately it just got rejected. And we resubmitted to ICLR, and the same reviewer literally found it, posted the same review again, and then it got rejected again. So that was super discouraging. But then we sort of forged ahead regardless, onto trying to understand why, or at least like what effect the data set kind of has on the outcome of your offline MARL experiments with your algorithms. And because, we had this feeling that the fact that everyone's using their own data sets was problematic and, led to bad science. So off we went, and by now there were quite a few new papers that had like emerged in the field. A couple of them adopted some like existing data sets. Like there was one that used OG-MARL here, and there's two, I think, that use some of the data sets from the multi-agent decision transformer paper. But the vast majority, which you can sort of see at a glance from the middle column, self-generated their data sets, which like to us is still worrying. And we also see that despite like self-generating their data sets, they typically like give very little information on the like how good the data set is, like in terms of the episode return of the samples in there. So just giving like the mean episode return in a data set, and then the standard deviation of the episode return as a kind of proxy for diversity. That's very common in the single agent literature, but like people weren't really doing that. So we just ran some like small experiments to kind of, prove to ourselves and to the community that like these things are probably important on like the outcome of your experiments. So like, I mean, this one's altogether not very surprising, but we generated a bunch of data sets with specified mean episode returns on like some SMAC environments, and then trained our algorithms on there. And as you expect, like higher mean episode return usually like resulted in a better final performance. Then we looked at the standard deviation, which like in the single agent literature is, like I said, used as a kind of proxy for diversity, and many offline RL algorithms benefit from more diversity. And here there was like a slightly more interesting trend than with the mean, we see that, you know, for the highest spread, it wasn't necessarily the best. There was kind of a middle where the data set was the best for the performance of the algorithm. So that pointed to maybe something interesting here with how data affects the algorithms. And then we asked ourselves, well, okay, if we, you know, construct a data set where the mean's the same, the standard deviation's the same, but we artificially make sure that the distribution of episode returns is visually different, which is what you can see in this histogram. So we've put into buckets how many episodes with the given episode return there are. So like the big orange peak on the left says that there are quite a lot of episodes that got 2,000 episode return in this data set, and then a whole bunch that got over 8,000 all the way on the right. And then with blue, you know, there's no episodes much more than 8,000 episode return. They're mostly around 6,000 and a couple all the way at the bottom. So we then train the exact same algorithm on like both these data sets, and then we see them converge to like dramatically different final performance, which we've found like quite just like interesting, because you might think like, oh, the MARL, offline MARL algorithm should have, like in the orange case, been able to focus on the really good data there at the peak, you know, past 8,000, but didn't nearly do that. It sort of flatlined after 2,000, which, yeah, points to there being like interesting thing going on here. We then went a step further and said, like, okay, if we make the data sets look the same, like visually, what happens then? So we took data sets for 5M versus 6M that we generated in OGMARL, and then we took another one which other authors had generated in their paper that proposed this CFCQL, the counterfactual conservative Q-learning. We then had subsampled our OGMARL one because it was bigger to begin with, in such a way that it ended up with this distribution that looked very similar to the CFCQL one, and had the same number of trajectories and about the same number of transitions, and then trained our two algorithm, like the algorithm on each data set again. It was, and oh, by the way, sorry, the IQL plus CQL is just my terminology used for independent Q-learning, but using conservative Q-learning. So that's the algorithm we used. And again, we see them converge to like very different final solutions, which was surprising. And we, you know, wanted to think, okay, well, then what about this data set is different? And one thing we came across in the single agent literature by Schweigerhofer is a measure of the, like a better measure for diversity, which he coined state action coverage coefficient. And we sort of extended this idea to the multi-agent case. It's effectively a measure of how many state action pairs are, like how often they're repeated in the data set. So you concatenate them together and then basically count how many times each pair is repeated. And we do this now with the state and then each of the agent's actions, like the joint action. And so what you end up with is this joint state action coverage coefficient. And what it's saying here is that in the CFCQL paper, they had a joint SACO score of 0.1, which says that only 10% of the transitions in the data set are unique. Like the other ones are repeated and like a number of times. Whereas in the OGMARL one, almost 83% of the joint state action coverage pairs are unique. So the diversity then should be higher. I'm not saying this is the reason it came to the final score. Like you probably need to like come up with better tests for this, but this is at least one dimension along which the data sets were different. So at the end of this, the takeaway was we don't really understand the effect of data on offline MARL algorithms very well, and more work needs to be done in this direction to understand it. And for now, the best thing we can do is make sure we standardize the data sets we use across the field so that we can control for these unknown effects. This was then written up into a paper we submitted to DMLR, which is the Data-Centric Machine Learning Research Journal, and sort of under review. So we'll see about that. This came with a host of sort of other things, like we took all the data sets we could get access to from the literature and converted them to the same API that we were using now in OG MARL, and then added everything to Hugging Face. And so now you can get access to the data sets we've created and a whole bunch of the ones from the literature. And they all use the same API now. And so it's very easy to get your algorithm to work on everything. We then open source these utilities we built to analyze your data sets, so that hopefully people now find it easier to report if they make a new data set on some of these properties that are clearly quite important. And the utilities for subsampling, where you can give a target distribution and it'll choose episodes from your data so that you can test under what conditions your algorithms maybe respond differently. Now we wanted to dig into, as a next step, why algorithmically maybe they're responding in this way to different data sets. So we wanted to find an interpretable game or something where we could experiment and try to get intuition for why we have these strange behaviors. And what we settled on is a polynomial game, which has been widely used before, and we try to set up a kind of offline polynomial game setup. So in a polynomial game with two agents, you can visualize the game on the plane like this, where the x-axis is the continuous action that agent X can take, and then on the y-axis it's the continuous action that agent Y can take. And then the reward they get, it's just a single step game, is the some polynomial of X and Y. It can, in this case, just XY, but it could be X squared times just Y. This XY game has also sort of been used a lot, but basically in the top right-hand corner, you have a high reward region, and in the bottom left-hand corner, you have a high reward region. But in the other two corners, it's a negative reward region, and the gradient field sort of points to walking up and then out to the side. Now, if we think about how you might set up a learning offline, or at least from a replay buffer, is you say, okay, the two policies, mu, because we're just using a deterministic policy, mu for y and mu for x in this top left-hand quadrant, is the point on the plane is the current joint policy. Then what happens is you sample a joint action from the data set, B, your replay buffer, and in this case it's AY and AX somewhere in the region. And now if you're updating the agents independently in response to that data sample, then you see for the X update, it updates its policy in response to that data point, AY. And given where AY is there, the best thing for X to do is to move to the left. And similarly for Y, it updates its policy with respect to what it sees agent X do from the replay buffer, and it notices it should go up. So importantly, they didn't update in response to what the real policy is. They're updating to the data they get from the buffer or from the data set. But then the joint update is exactly in the wrong direction, and they go up to the left-hand corner instead of improving their policy and going down. And this looks like this if you make a data set that uniformly covers the whole plane, and you sample batches of 32 mini batches, and then you aggregate all of that across a mini batch and then update. You just sort of randomly bounce around given the small bias in each batch, and the agents sort of don't learn anything. But this may feel sort of contrived, but the truth is that MADDPG, as I'll show now, like works off online when we use a replay buffer. But if you do exactly this with a static data set, then it clearly doesn't work. And this is exactly what a lot of people in the literature are just doing. They're taking MADDPG, thinking that somehow because you have centralized training, that you've then just resolved the issue of like the non-stationarity problem is just like fixed. And we show here that it's not. Like here in this plot, we wanted to show like how, from this perspective, like online MADDPG works. So you should look at each column in turn. They have increasing sized replay buffers. And with the smallest replay buffer, we then at the bottom give the final buffer state. So you can see that the data is very concentrated near where the current joint policy is. So that means the batches you're sampling from there reflect relatively closely what the current joint policy really is. And so then the gradient, the multi-agent policy gradient you'll get from it will be like a relatively good one and move you in the right direction. But then as you make the replay buffer bigger, you have more and more stale data, which serves to sort of send the agents making bad updates. And then the bigger the replay buffer gets, you can see like how it's more perturbed. And it's also reflected in the reward curves you see in the middle there. And now offline MARL is just like the most extreme case of this. So in this simple setting, like we just proposed a pretty intuitive fix. Suppose you could measure how far a data point in your data set, like a transition, how far the policy that generated that transition is from your current learned policy. Then you can prioritize looking at data that's similar to what you're currently doing, or like similar to what, so that your teammates and stuff are behaving as the current learned policy is. And in the plane like this, it's very easy. You just measure like the Euclidean distance between 2 points, and then you make the priority of sampling, like prioritized experience replay, greater for samples nearby. And then that sort of fixes the problem. We then looked at just like a higher order polynomial game, and this thing has sort of got two big peaks, where the true maximum is at that red point. And in this like contrived example, we just put all the data on the optimum, and then MADDPG gets there. But then what we do is we like make the data set simply, it's got the mean is at the correct place, the correct joint policy, but there's sort of normally distributed around it data. And then we find that actually deflects the learned policy of MADDPG slightly, whereas when you prioritize samples nearby, it does eventually get to the right place. And as you make that spread bigger, it's still centered around the correct mean, but then the final point that MADDPG gets to is increasingly at the wrong place. Which, yeah, we felt in a toy example shows like the failure of even a CTDE algorithm, never mind like an independent learning algorithm in the offline MARL case. You can basically think of like it can independently improve upon, the part of the reward function which it's like agent 1 is responsible for. It can optimize well, improve that score, and similarly for agent 2. But if there's some part of the reward function that depends, like is coupled between them working really hard together, in the polynomial game, it would be, an interacting term. Then MADDPG like fails to be able to handle that offline. We then tried to like demonstrate this in a higher dimensions, but it's a bit harder because now you need to like come up with a good way to measure the distance between the learned joint policy and the behavior policy, the one that made the samples. So this work can be improved a lot, but like what we came up with at the time was just like in a trajectory measure the like just Euclidean distance between all the actions in that trajectory, and then take the average, and then say like if that's small, then you know, the policies were probably quite similar. But if that distance is big, then they were very different. And then we prioritize the samples in the data set like that. And then what this graph shows is the average distance between the samples in your batch, so the samples you drew from the data set, and your current policy. And what we see is that in blue, which is the one with our PGAP idea, that distance gets smaller, about 10% smaller than otherwise, which means those samples are indeed closer, which is what we were sort of hoping to achieve. And in this case, we do see like more stable convergence, and convergence to like a higher score. That's what's in the bottom, the normalized scores on the x-axis, and then the spread. But yeah, definitely need more work, like to verify that, like make sure this works well in harder settings. So that brings us then to like our next attempt at trying to benchmark the field, now that there was like quite a lot more work. So if we went again to review the literature, and we chose to focus on like the papers that had been accepted at like the big conferences like NeurIPS, and we settled on these. And we first dug into what environments they were using, and we see this worrying thing where you know, despite all using SMAC, they tend to then choose different SMAC scenarios, to the point where like there's no common SMAC scenario between all of them from all of these, which yeah, makes things hard to compare across. And we then dug into like the evaluation methodology that each of them used, and you know, noticed that it's very inconsistent there. We then looked at the baselines people use. So oftentimes they will propose the algorithm, and then because there's not like a agreed upon standard baseline that people are using or implementation, people often talk about this multi-agent conservative Q-learning thing. But then when you scratch under the surface to see what they mean, you notice that they typically mean some sort of MARL algorithm, and then they plug CQL into it. But that MARL algorithm varies across papers. So sometimes it's MADDPG with Gumbel softmax, and other times it's QMix, or something else like DOP or something like that. So yeah, that's not consistent. And then another practice is people won't share their baseline. They may, if you're lucky, share their algorithm, but then not whatever baseline they sort of made. And why is this important? Well, we just did this experiment where we made two different MACQLs, the one with MADDPG and Gumbel softmax, and one with QMix. And not only do you find that like they perform differently, but they don't consistently, like one's not consistently better than the other. We see that MADDPG was the best across 8M and 2S3Z, but then all of a sudden in 5M versus 6M QMix definitely does a lot better than MADDPG did. So this was tough. And then we did like a big meta-analysis of the reported results across all papers. We have this notebook which you can go through, and we do the statistical tests which were done in the benchmarking paper from this lab, the MARL benchmark paper. And yeah, like what you find is sometimes results like these where they'll like highlight their algorithm as having the highest mean, but I mean, they're basically indistinguishable from the others, especially when you add in an error bar. And all of this, the sort of non-standard environments, self-generated data sets, self-made sort of baselines, all of this together makes it really hard to compare across papers because there's like no common axis that is standard across all of them. So what we decided to do was to take each paper, try to get their data sets. So to be basically included in this benchmark, we had to be able to get your data sets. We converted them to an API that our simple baselines from the start of the talk, the IQL, like the independent conservative Q-learning, and the independent TD3 plus BC for continuous action spaces, such that we could run ours on there. We then, to the best of our ability, did exactly what they did in their evaluation as they did it, and then performed statistical tests between our result and their reported results. And what we end up with is this plot, where on the x-axis are all the different data sets we could obtain. We then normalized all of the reported scores for each data set against the state-of-the-art score, so usually the algorithm the author proposed, and then plotted the score our baseline got on that data set using the same methodology. So from our perspective, we gave them every benefit, every advantage, but still we find the surprising result where on all the green region is they're the mean of our runs over 10 seeds is higher than whatever they reported across any of their algorithms. And in the yellow, our mean fell slightly below whatever they reported, but when we did the statistical significance tests, we land very basically equivalent. And this was a sort of pretty breathtaking result, and one that we now just recently presented at NeurIPS in the datasets and benchmark track. So eventually we got there, and all of this, all of the work that I've presented now has been constantly being added to the offering within Off the Grid MARL, the OG MARL project, which is something I maintain along with the rest of the team and work really hard on. It includes all of the baselines that we used for this. It easily plugs into all of the data sets we generated and have now uploaded to Hugging Face. So it very easily pulls the one you want and then runs the baseline over it. Comes with a bunch of useful utilities like Hydra configs, weights and biases logging, along with I suppose me trying to be very active on the issues and discussions. So there's various conversations going on there where I try to be as helpful as possible. And it's very fast because we implemented the baselines in such a way that we could JIT compile the code. And so I think, the experiments can run really quickly on the data sets. So in conclusion, it's been a long and winding road towards standardizing the field of offline MARL. And we've approached it through a number of axes, through the data sets, through the baselines, and looking at the evaluation methodologies. And I feel we've made significant progress, and I hope that if it's adopted, the field will continue to make great progress, and hopefully it'll just be sort of more reliable, and therefore we can make faster progress. And I feel very excited about the field in general. I think it's a fruitful area of research with many open problems, and that's pretty much it. I thank everyone for listening.
Cool, thanks so much, Claude. This is, I guess a lot of these results are super surprising. It honestly feels weird that people are sort of creating their own data sets where this is sort of the one field in RL where people can actually use these standardized data sets. I imagine if everyone was creating their own CFAR 10 for supervised learning experiments, it would be super weird. So thanks for telling us about all these challenges in offline MARL. I'll hand over for some questions. Does anyone have any questions? If not, I'll sort of start off. If you have any questions, raise your hands. If not, I will ask some of sort of my questions. I'd say the first one is when you discuss sort of the coordination failure in offline MARL, do you think like that it wouldn't happen in online MARL, or there's something that makes it less likely? I know, I think you briefly spoke about it, but I didn't completely understand.
I mean, it's all just like a manifestation of the non-stationarity problem. And I think like when you see those replay buffer experiments, you basically see why on policy MARL algorithms have been so successful, like MAPPO and IPPO and stuff, versus the more off-policy algorithms, where you usually have to like shrink your replay buffer down to make it perform well, and then you have this tension where, like, at DQN you might want a bigger replay buffer in the single agent case, it helps your neural network, but in like MARL it destabilizes training, and you see that very nicely in the polynomial game. And because offline is like the most extreme version of that. You have the coordination failure pop up unless you do something smarter, and CTD, like centralized training, and the way MADDPG does it, like, isn't enough.
Okay, cool, makes sense. If anyone else has a question, raise your hand. If not, I'll continue asking my questions. I guess the other question is more sort of a broader question on RL and multi-agent RL. In a lot of sort of the empirical work, you see these massive tables with a lot of different algorithms compared, and it sometimes feels difficult to fairly compare every algorithm and not do it in a way that, I guess, favors your new method. Did you have similar challenges? Because I imagine, like, there's some hyperparameter space where algorithm X does well, and it becomes quite difficult to like fairly compare these offline algorithms, especially across data sets and across different implementations and tweaks.
It's a really hard problem just in general, and in RL, because to be fair, you ought to like make sure you have the best, most reliable implementation of the algorithm you're trying to compare against, be that your own like re-implementation or like getting their implementation, I guess. And then spending like as much time as you spend on your algorithm, tuning it to make sure you're fair along that dimension. So all of those things are a massive challenge and remain so. It's just we were falling, like the field I felt like was falling short of even like the bare minimum, where, if your code isn't available, then I can't even try to faithfully reproduce it, I feel. And so while this certainly doesn't like fix everything, meeting some of these minimum criteria will go a long way to help. And then I really appreciate like the projects where people have try to do benchmarking or provide open code like CleanRL or something, and spend a lot of time on each algorithm because they don't have a vested interest in like their algorithm. And that's why I think more venues like the Datasets and benchmark track at NeurIPS would be good for the field, where work like that can get rewarded. Because I think, this work probably wouldn't have made the main track at NeurIPS. It like certainly wouldn't have. It would be like, this isn't novel enough. But they created a space where then it was the right place and rewards us for doing that kind of work, which I think is very valuable.
Okay. Yeah, I think that also leads to, I think we had Adam White a couple of weeks ago, and he spoke about don't waste your time, like don't waste people's time in research, like make sure what you're doing is correct and make sure that your algorithms are actually useful, because you don't only waste your own time, you waste like other people's time trying to like re-implement and sort of reuse your method. So yeah, I think that's a great point. I guess final question from my side. You spent like quite a few years on the offline MARL space. What I guess future directions are you the most excited about? Like now that you've like worked on a lot of these problems that you mentioned.
Yeah, well, I think that in the offline RL space at the moment, like Sergey Levin and them have released a couple papers where they've really scaled RL like more successfully than has been done in the past. Like the neural networks we've typically used like remain pretty small, and you could argue that that's probably why like generalization is like been less impressive than in other fields like LLMs or something where the networks are huge. But now we're seeing them like successfully implement pretty big RL networks and demonstrate like some early sort of scaling law type things, which I think is exciting, and will hopefully go a long way in getting RL to generalize better out of our toy settings. And I mean, doing a similar thing for MARL would be cool.
Cool, very exciting. Okay, if anyone else doesn't have questions, and I think we'll just give Claude another round of applause. Thanks so much for joining us, and thanks for speaking to us about offline MARL. Everyone else, hope you have a good day further. Bye.